Lecture 5.2, the characteristics of a capacitor, its capacitance. So what we want to do is derive capacitance, but only looking at the details of the capacitor. Earlier, we did the capacitor equation, which tells us about the ratio of charge to voltage being the same and defining that as a proportionality constant. We want to look at the physics. And so what we'll start off with is that we assume two large parallel plates. Where we could then say that the electric field of the parallel plates is a very good approximation to the infinite plates or infinite planes. So what that really tells us is that we're looking in the middle of the capacitor. So drawing out our capacitor, but this time I'm going to be looking at the field so I have my upper and lower plates. I assume that it's a charged capacitor, so it has some type of charge in the lower and the bottom plate. And what we know here is that if these are infinite plates, we can then produce two electric fields that we have to look at that. So in other words, I have a positive field pointing away from the positive plate. The negative plate has field lines that point towards the negative plate. And right away, because they're the same size, you can see here is that the field here has to be 0. The field here has to be 0, but not true for the capacitor. Now, just as a reminder here, this here has the area A. This right here has the plate separation, little d here. And so what we're finding here is that in between the plates, we're going to have a field. So now I'm going to focus on the field right inside. And so when I look at this, I have two fields that are going to add. And then the value for an infinite plane is then 2 divided by 2 epsilon naught. And so then finally we get the charge density divided by this guy right here. That's what the field is. So from the electric field, we can make the connection between the charge and the potential. So from this E field, a connection between the charge on the plates and the voltage of these parallel plates is made. And so here's what we see. So if I'm looking at the field inside, we can also write this as the voltage of the parallel plates divided by D. But the capacitance equation depends only on the voltage. So then I can rewrite the voltage of these guys as it's going to be dE inside. Now, the other thing that we can look at is that by starting with the electric field, we know that this is the same as eta over epsilon naught, but that's just the charge per unit area divided into by epsilon naught, or I can solve for the charge in this situation, and this will then be epsilon naught A E on the inside. Now, the capacitor equation shows that it is true that the capacitance is the charge divided by the voltage. But if we put in these other terms, you'll see that there's a cancellation of the electric field. So this cancels out with that. And so now we have the details here. So now the full capacitor equation now reads like this. The capacitance of a parallel plate can be written like this, but that's not in terms of the characteristics of the capacitor. What defines the capacitor? It depends on the dielectric inside. It depends on the area, and it depends on the plate separations. So when I look at this, what I see is that this thing is for all capacitors. But this guy right here, this tells us about the characteristics of a parallel plate capacitor, which is unique. So once again, this is the capacitor equation. But we now see that it has two pieces. So what I would say is that this is the most important equation for the parallel plate capacitor. And without any doubt, it's the most important capacitor that we study. Now, I want to start to interpret this one because there's a lot to unfold here. Okay, there's a lot to unfold. So now let's talk about the interpretation um, of the capacitance of the parallel plate. So when I look at this thing, what I'm paying attention to is not charge over voltage, even though that's correct. So the first thing I want to focus on is that note that capacitance of the parallel plate capacitor does not depend on Q and the voltage, but only on the characteristics of the parallel plates. Right, so when you look at this in detail, it reads like this. It says the capacitance is going to equal to the dielectric material times the area divided by the distance. In other words, this is about the dielectric material, which we identify as epsilon, times the geometry of the capacitor. And in this case, the geometry is the area divided by the plate separation. So when I think of capacitors, this is what I typically think of right here. I think of this equation because it tells me about the capacitor. In other words, its characteristics. So what we want to do here is that we want to analyze this equation. But it turns out that we need more information to deal with the dielectric. So here, we will only address the geometry of the capacitance. And save the dielectric material for another lecture. It's because we're going to have to really spend a lot more time trying to figure out what we mean by the dielectric when it's in a capacitor. So that means we have to address the area and we have to address the plate separation. So let's look at that. So here we go, 2. So we're going to talk about the area, A, dependence of a capacitor. So as we've been saying here is capacitors store electric charge. That's what they do. So to give you a sense of that, I'm going to give you an analogy of cinephiles, in a movie theater or in a cinema. Okay, so here's my analogy. Maybe I should move this down just to be a little bit more organized. So the size of the cinema determines the capacity to seat these cinephiles. Oops, that's supposed to be an H. In a similar manner, capacitor plates store charge onto plates where each charge effectively gets their own seat on the plate. So let's look at capacitors. I mean, let's look at just areas. So if I look at areas here, I'm seeing something like this. So if I have a plate that looks like this, so here's my plate. And then I'm going to divide these into spaces where I can place infinite or minuscule amounts of charge. So I could come in here and I could just say, yep, I'm placing a charge here, I'm going to place a charge there, here, etc., etc. So in this case, if I have a smaller area, that tells me the capacity to store charge is small. Therefore, it has a smaller capacitance. And I think I'm going to move this further down. So what we're really saying here is that in this situation, the capacitance is small because the area where I'm storing the charges are small. Now we can have a larger capacitor. What if I have a capacitor or something like this? That's definitely a larger one. So if I look at this, you could see I could come in and I could do my grid marks again. And you could imagine that each little square is going to have these number of available seats for these electrons or these positive charges. So if I start to put them in, you could see that I could come in here and I could place a lot more charge. In other words, if I have a larger area, then the capacitance to store charge is now going to be large. And if it's large, that means I'm going to have a larger capacitance. So I have a larger capacitance because it's directly proportional to the area. And that makes sense, right? So now let's go to the next one. And this is going to be about the plate separation little d dependence of a capacitor. Now this one requires a little bit more work. So the one thing that we should think about here is that assume once a capacitor is charged and removed from the source of energy, the battery charges do not move off these plates assuming no dielectric breakdown. So mathematically, capacitance is inversely proportional to plate separation. Little d. So what does that mean? Well, let's set up two capacitors, one that is closely spaced and the other one that's far away spaced. So I'm going to imagine that we have a capacitor like this. And the charge is going to be the same in each situation. So in other words, in this situation, if this guy has 5 charges, then this one's going to have 5 negative charges. And we're going to see here is that this distance right here is going to be our plate separation. So now what I want to compare this to, I want to compare it to a capacitor that's farther apart. So when you're looking at this here, they have the same amount of charge, but the big difference between these two is that the separation of these guys is really large. Now, in each situation, we're going to say that Q is equal to a constant. And here, that has the exact same amount of charge. So what does it say mathematically? Well, if I look at the capacitance, they tell us that I have epsilon. By the way, I did not put that in here, which I should have. So here's our dielectric right here. So epsilon does not change. This epsilon does not change. So it's going to be fixed here. So in each of these situations, the area is the same. But the big difference is the plate separation. This is tiny. That is large. As a consequence, mathematically, that's a large capacitance. This is a small capacitance. So what does this tell us? It tells us that if I have a small plate separation, then that tells me I have a higher capacitance. But a higher capacitance means that you have more stored charge. The same thing happens with this one. The fact that there is a large plate separation, that means that this has to have a smaller, or maybe not smaller, but lower capacitance value, which means that it stores less stored charge here. I mean, that's what it looks like mathematically, but I have no idea what that means. So unfortunately, this mathematical result does not give any physical insight. Why the capacitance changes with sorry about that, with the plate separation. To see why it is, so to see physically why this is, we go back and look at the work done. So here we go. So I'm going to deal with electric fields for a moment, but that's going to tell me about the potential. So the work done by the electric field as a charge moves from a lower to a higher electrical potential energy is like this. So I'm just going to come up here and I'm going to do this. I'm going to copy this. I'm going to bring this down with me. And I'm just going to paste this guy right in here. So I have this situation. So let me adjust this just a bit here. And what I'm going to do is that I'm still going to have the same plate separation. And of course, in here, I have my dielectric in between. I don't have to have, some dielectric. I could use air, and that's what I'm going to choose to do. To just stick to the simple stuff. This is a bit small, so I'm going to bring this down just a bit here. And so here's what I know about the situation. I have a plate separation. Now I have a test charge. Here's my test charge. And what I'm going to do with this test charge is that I'm going to start moving it upwards. So what do I know happens? Well, I have an electric field, but my displacement is in that direction like that. So if I calculate the work done, the electrical work is minus Q, the integral of E dot dr. And of course, this will be for a constant field between parallel plates. This will be minus QE delta R. But according to the work energy theorem, this is minus Q delta V electric. In other words, if I'm going to look at the work, right? So then the work done per charge is the voltage. Right? That's what that's really telling us right there. So what this does here is it's going to allow me to reinterpret what do we mean by capacitance. Now, we reinterpret the capacitance as the amount of work per charge done. So I could either say how hard, and when we say hard, we really mean work. How hard is it to move charge from one plate, let's say the lower plate, to the other? In this case, it's going to be the upper plate. How hard is it going to move? It also tells us about the charge separation, right? Another way of saying the exact same thing we could just say is how much charge difference. No, I think I want this in capitals. How much charge difference delta dq is there between the two plates for a given voltage. Of course, voltage across the plate. So I want you to think about this in sort of like picture terms. So I need two situations, and I'm going to look at both of these guys simultaneously. So let's look at that. So I have two plates. And I'm going to keep their separation the same. And so when I'm looking at this guy versus this one, in this case, I'm going to say that the separation in this situation is then going to be D. You know, I'm going to move this over here. So when I look at this, I'm talking about the separation of charge. So what I'm looking at here is that in this situation, I have this amount of charge on the plates like that. So I'm going to say that this charge difference is going to be a small charge difference. What I'd like to do is I'd like to copy the exact same thing, and I want to place it here now. But now what I'm going to do is that I'm going to separate the charges. But no, I'm not going to separate the charges. I'm going to add more charge here. So when I look at this guy, this one has a bigger charge. Okay, that has a bigger charge. So in this situation, if I have a smaller charge difference, and what I mean by that is that I talk about Q being the charge of the upper plate minus the charge of the lower plate, we're going to see that this tells us that we're going to have a lower capacitance. Now let me move this over here a bit more. In fact, I think to try to consolidate my space, I'm going to talk about if this is the charge difference, I'm going to say it right here. I'm going to have a lower capacitance. It's a lower capacitance since less charge is on the plates when work is done on a test charge. So in other words, if I have a test charge here, and if I have a test charge here, and what we know about the test charge is that now we're going to be moving it up in this field because it has less charge. It takes less work in order to move it here. Here, this is a larger charge difference. And as a consequence, this has to have a higher capacitance since there's more charge on the plates. And remember what I said, how hard it is to move charge from one plate to the other is another way of defining capacitance. So now let's look at this slightly different here. So now let's bring a difference in plate separation. And then we have to ask the exact same question. So what I'm going to do is that I think I'm going to look at this guy right here. So I need two different plate separations. So here's what I'm looking at. This is going to be my first case right here. And what you're going to find is that I am going to fix the charge here. In other words, I'm going to say that this delta Q is going to remain fixed. So the separation between these two charges is going to be the same. Now what I'm going to do is that I'm going to keep this separation of charge exactly the same, but the big difference here, so note we've already said that we're going to keep the charge exactly the same. The big difference here is that now I'm going to separate these guys. So now if I drag this guy down here, we clearly see that once again, I didn't do anything with the charges. They stay fixed. But clearly in this situation, we have a larger separation right here. So if I look from here to here, I now have a large separation. So then we ask the same question. If the plates are close together, then the charges only have to move a small distance. And that doesn't take that much work. So if plates are close together, the charges only need to move a short distance. Which doesn't take much work. So what that's telling us here, so if I now use the capacitance equation, is that in the language of capacitance, is that if we can move more charges between the plates, capacitance is higher. So if I can move more charge, then the capacitance increases. So in other words, we're saying here is that capacitance increases when you decrease plate separation. Well, I could say the same thing right here. So if I bring this down just a little bit more, I could say that if the plates, or if one moves the plates farther apart, it takes more voltage to move the same amount of charge. It takes more work, right? Yeah, right. It takes more voltage to move the same amount of charge, since they must move a farther distance. So for the same voltage, as before, less charge is moved, and capacitance is lower. In other words, capacitance decreases when you increase plate separation. So the last thing that we want to talk about, so just remember, this is slippery, right? This is not an easy concept. But the bottom line is, can you move more charge or not? So as the The final thing that we want to look at is that I want to look at the units of capacitance. So a unit of capacitance is a unit of charge over a unit of voltage, which is a coulomb per volt. And this, by definition, is called 1 farad of capacitance, which we typically write as 1F here. This is huge. Okay, this is a huge capacitance. So to just give you a sense of what we mean by that, so we could say is what is the size of a 1 farad capacitor if the plates are separated by 1 millimeter. So when I say size, I mean area. So here we go. This is sort of like a crazy thing here, but you're going to see what I mean by that. So if I have a capacitance, and we're going to use air as the dielectric. So if I put in these numbers here, what I'm saying here is that I know that the capacitance is equal to 1 farad. This is 8.85 times 10 to the minus 12. And this is typically in units of farads per meter. And then we're going to say that D here is 1 millimeter, which is really 10 to the minus 3 meters. So if I put this all together and I calculate the area, so if I look at the area, then this is going to be the capacitance times little d divided by epsilon naught. And if you calculate this number, it's about 10 to the 8 meters squared, which is about 10 kilometers squared. Note, this is about the area of Santa Cruz County. That's huge. No, not the area of Santa Cruz County, but the area of Santa Cruz City. It's a humongous number. So if you look at this thing, the one parallel plate, if I look at just one parallel plate, what's the area? That's effectively about 6 miles on one side and 6 miles on the other side. That is crazy.